Hello, PreCalc. This is after Monday. It's the 8th after Monday's class, and we are studying a tiny whiny little topic. So I can whine. It's so tiny whiny. We're going to study rigid and non-rigid. Am I a good whiner? Till I'm in a mood. Rigid and non-rigid transformations. Alright, no whining from you because I've already done the whining. Let's look at what I mean by that. Transformations are when we take our 8 parent functions and move them all around. We love to do that. So let's say, for example, we have a parent function. Do you recognize this one? I'm dotting it in because it's not the real answer. It's going to help us to get to it. It's y equals absolute value of x. And a rigid transformation is something that I already mentioned via video, such as like this. If you recall, these numbers mean a certain change in the transformation. You all have the sound on. You could take notes without listening to my voice. So you're not going to know how to do it tomorrow. You have to listen and take notes. Up to, and this negative will tell you when the value is hugging the x-axis inside the function, then this is the opposite of what you might think. It's left-right, so this is a right 3. So we've had this before when we studied exponential and logarithmic functions. So this sort of rigid transformation is a review. So we're going to go to the right 3 and up 2. So right there, and this function is now going to appear at this spot. But notice the shape is the same. So I picked it up and just moved it as it is over 3 and up 2. So we call it rigid because it is staying the same. It is like a rigid graph that's not been changed except in its position. The shape is identical. So now the tiny whiny thing we're going to cover tonight is non-rigid. Non-rigid transformations. All right, so these occur when the function, any function, I'm teaching it with the absolute value function, but it can be any function, any of our parent functions, has a constant multiplied times the function. And another example of a non-rigid transformation is when a constant is multiplied inside of the function. So we'll go over both of these in regards to the absolute value, and I'm trusting you will be able to do any parent function after this example. Suppose we take one of these, say we say 3 times the absolute value of x. So I want to know how that changes the original graph. So here is the original graph dotted in, and it turns out that when you have a value here, if that value, we'll call it c, is greater than 1, then it causes a vertical stretch. And a vertical stretch is like this. Maggie gave me this cool thing, and it was very stretchy. And since it's always getting used and laying around, I found a little spot on it, and I put on an absolute value function, and it's going to, I'm going to vertically stretch it, and you watch the graph. Isn't that cool? So the more I stretch it, the more it looks like it's closing in on the y-axis, like that. And we could actually figure out the actual values. Like if this used to be 1 over 1 up, then once I put a 3 there, it would be 1 over 3 up. But I don't really care to get the exact graph. I just want to see that you see that the original function is stretched vertically. So it's going to be, I guess, taller. Well, I can't really say it's taller, both are infinite, but it's skinnier, it's closing in on the y-axis. All right, now what if c is less than 0? I mean less than 1, sorry. Then we have a vertical shrink. Alright, so the way I can demonstrate a vertical shrink is I can start it like it's like this and shrinking in the vertical direction. So I'm going to take it and squish it in vertically. So here it is, say that's the original function, and when I squish it in vertically, it gets shorter and fatter. We'll say at least fatter. So a vertical shrink, or keep the vertical stretch in view. If we start with the regular function, and then we get, alright, so that's called a vertical shrink. So vertical stretch, where I take this graph and I stretch it vertically, and a vertical shrink is when I press it, shrink it in the vertical direction. Alright, so again, when I ask you to graph, and this is what this one would look like, say, because c has to be less than 1, so I'll have something like 1/3. Alright, so do you see that's this pattern? I haven't gotten to this one yet, so we'll put that one on hold. These two represent when the change is outside the function. When it's greater than 1, a vertical stretch, and when it's less than 1, it's a vertical shrink. Alright, then the other part is y equals f of, I don't want my absolute value yet, I want to be more general first. Y equals the function, but the factor that we're adding is inside of the function. So when that's true, for example, y equals the absolute value of 3x. So notice the change is within the function. And up here, it was outside of the function. So when that happens, this causes, if the constant that was the factor was greater than 1, it causes horizontal, guess. If this one caused the vertical stretch, does it surprise you that this causes a horizontal shrink? So that's when c is greater than 1, such as this. So let's come over to our little thing here. So this time I'm going to start it, pretend that the graph starts like this. And I'm going to, this time in the horizontal direction, I'm going to shrink it. Let's look at that again. Here's the original, and I'm shrinking it in the horizontal direction. So my thumbs are coming together, shrinking it. Did you see what happened to the graph? Alright, hopefully you envision this. And when I shrunk it, one more time, So it was like this, and when I shrink it in the horizontal direction, it became closer to the y-axis. Did you notice that a horizontal shrink is the same as a vertical stretch? See? And our sock thing over here verifies it. Alright, one more. So now I'm going to do y equals f of cx, where c is trouble tonight. C is less than 1. So I'm going to have something like y equals the absolute value of 1/3 x. So the constant, the factor that's been added to the function, is right inside of the function. And guess what it causes? A horizontal stretch. Alright, so let's come over here and see what that looks like. Here is our regular function, and now horizontally, this way, I'm going to stretch it. Alright, I think you can see what's happening to the picture. Alright, when that happens, you can see then that a horizontal stretch is the same as a vertical shrink. So how many people in the world know that? Alright, can you put those ideas together next time in order to graph something like, it's like that's the square root function? Can you figure out what it would look like if I did this, or this, or when the change or the factor is inside of the function? Alright, I want you to be able to work on that, and we'll talk about it tomorrow. So think that through. What will that do to the picture, the original picture here, the original function, unaltered, if I put a 3 in front, a 1/3, a 3 inside the function as a factor, or a 1/3. Alright, I hope this video was watched by you and not you by it. So you watch the video, not the video watching you. And this is just a test to see who actually is listening, because you could take notes without listening, but I don't think you'll know how to do it very well. So I'm going to give a secret word, and if you hear this word, you can write it on your notes, and you can erase one of the homework problems. The secret word, or it might be 2 words. The secret phrase is key fob. Key fob. I can't write it because I'm seeing who's listening. Key fob, write it down, and you will get a homework problem off. Alright, that's it for tonight. I hope this tiny whiny lesson didn't grow too long, and I will see you in the morning. Carry on.